So we're going to be looking at routing versus switching, just a recap of everything we've been looking at up to today. So switches do all their work at layer 2 and they need redundancy at layer 2 and all that sort of stuff, and routing does all their work at layer 3. It's all about networks, it's about accessing networks. Static routing and default route. Routers need route tables. They need to know how to get from A to B. So in this scenario, we've got two networks on the left, two networks on the right, and the default and the route to the internet. So realistically, a couple of static routes on R1, a couple of static routes on R2, everything else should work fine. Perfectly okay for a small network, but networks grow, networks need more complex, so typically dynamic routing will be beneficial. So in this scenario, exactly the same setup, but now we have dynamic routing. So router 1's running a routing protocol, router 2 is running a routing protocol. They're sharing information amongst themselves dynamically. Networks go down, networks come up, add new networks, everything's taken care of automatically. Configuring single area OSPF. We've got router 1, handful of networks, router 2, handful of networks. But you know something a little bit different about router 2? The wildcard mask is all zeros, meaning we're advertising just single host address. So when you're on router 1, if you were to ping 172.16.2.1, you'll get a response. But if you tried to ping 172.16.2.50, so if there was a PC plugged in, you wouldn't get a response because it's only advertising the host address. Typically useful for loopbacks, but in a real world environment, I would recommend the setup like R1's got, where you're actually advertising the entire network. So, useful commands. You've used them all before, you're going to use them again. Show IP OSPF neighbors. See what our adjacencies are. Show IP protocols. See what we're advertising. See how many areas we've got. Show IP OSPF. Let's look at OSPF in more detail. Show IP OSPF interface. Talks about what interfaces are being talking with OSPF. Show IP OSPF interface brief. Another useful command, similar to show IP interface brief, but this is more about the routing protocol. And of course, all these commands, show IPv6, exactly the same command. So, talking about IPv6, remember that when you're configuring IPv4, you use network statements. When you're configuring IPv6, the commands go on the interface. So, and with IPv6, you've got to have a router ID. No router ID, and OSPF just refuses to work. So we set up the OSPF process, IPv6 router OSPF 10, give it a router ID, make sure our bandwidth calculation is correct, and then in each interface, we set up IPv6 OSPF 10, area 0. Show IPv6 OSPF neighbor, show IPv6 protocols, show IPv6 router OSPF, show IPv6 OSPF interface brief. Exactly the same commands for IPv4. This is just the IPv6 version. Now, point-to-point link are our serial links, typically between two routers. Broadcast multi-access is an Ethernet segment. Non-broadcast multi-access, frame relay. We used to do a lot of frame relay, but now we don't do any frame relay, but you still need to know that it exists. Point-to-multipoint could be frame relay, hub and spoke technology. And virtual links. We don't really talk much about virtual links. In this version of the CCNA, it's mostly a CCNP. But virtual links are where you've got a couple of areas and an area can't physically connect to area 0. So you have to create a virtual link through another area so that you can stretch a bit of area 0 out to that other link. This is the reason why we have the DR-BDR election. As you can see, we've got 4 routers. If each one of those routers had to have a neighbor adjacency with all the other routers in the network, then all the routers would need 6 adjacencies each. Add a 5th router on there and it explodes again. So this is why OSPF is a very powerful routing protocol, but it can be very dangerous because of excessive flooding. When OSPF's got some work to do, it can literally saturate the whole network with its own information. So, recap of the DR-BDR election. There's a boss in charge of all the networks on that particular multicast, and there's a backup. All the others are called DR others. Now, when they've got information to say, so the DR others send information towards the DR BDRs on 224.0.0.6. And when the DRs have figured out what they need to share back to everyone else, they send it out to everyone else on 220.0.5. One of the ways I like to remember it is that DRs are important. So they're only going to listen for 6s. So if you've got something you need to tell the boss, then you tell him using a 6. And when he's got something to tell you, because you're an underling, he's going to tell you as a type 5. Remember too that the DR-BDR election is only for multi-access networks. Frame relay still needs it, but you have to trick it with the neighbor statement. And point-to-point and serial connections do not have, both ends are DRs. Adjacency tables. Show up your OSPF neighbor. Very useful command. If we can see on R1, we've got 2 neighbors. One's a DR, one's a BDR. On router 2, we've got 2 neighbors. One's a DR and one's an other. And on router 3, we've got a druther and a BDR. So you can sort of tell, it's a bit of a backwards way of thinking about it, but if you're ever not sure of your own state, you do show up your OSPF neighbor, and if you're on router 3, you've only got an other and a backup designated router. So therefore you must be the DR, because that's, if you can't see the DR, then you're the DR. The DR-BDR election process. Its primary election information is the priority. So all you have to do is just set the priority. You've got 4 routers that can all see each other via Ethernet. Go to one of the routers, set the priority to 10. He's going to be the DR all the time. There's a bit of a trick question in the exam. They give you a picture with a couple of routers and they've set them all to priority 0. When they're all priority 0, none of them can be elected DR, so OSPF is broken. But by default, they're all priority 1. So you need a tiebreaker. The tiebreaker is the router ID. The highest router ID becomes the DR, the second highest becomes the BDR. The router ID can be set manually, and it's often recommended to do so. If you haven't set it manually, it'll leech the IP address of the highest IP address of any loopback interface. If you've got no loopbacks, the router ID is determined by the highest active interface. And remember that in IPv6 it cannot do it manually. Sorry, it cannot do it automatically. You must set it manually. When the DR fails, the backup designated router takes control. And it will stay that way until the DR comes back, because every time there's a hellos come out, they say, hey, my priority's bigger, and they'll take over. Now, you can reset the OSPF process with clear IP OSPF process. Works great in a lab environment because everything recovers in a second. If you do it on a real network, you will have problems because OSPF will go into panic mode and it will take seconds of OSPF spamming the network to bring itself back to health again. So don't issue clear IP OSPF process in a production network unless you expect and you're happy with a good maybe 5 to 10 seconds of 0 network traffic during that time. Alright, propagating a static route. Best command ever. Default information originate. 5 years ago it used to only be for OSPF, and then RIP brought it on board and EIGRP still doesn't use it, but I can pretty much guarantee in the next 5 years, all routing protocols are going to be used default information originate, because it is what it means. The default information, your default gateway, is originated from this router. It's exactly the same command for IPv6 as IPv4. Remembering that once you redistribute that static route into the OSPF process, that router is now an autonomous system boundary router. Timers. OSPF has the actual timers in every hello packet. So if you start playing with the timers, you've got to make sure you change them everywhere, because the hello and dead timers must match on every router, because the actual values of those timers are in the hellos. So if you've got routers that won't form an adjacency, that's the first thing you should check. The hello and dead timers haven't been changed, or they're all the same. OSPF supports authentication for the routing updates. So by default, there's no authentication. You can add just a simple passphrase, but no one uses that anyway. Or you can use an MD5 hash. Remember that we're not encrypting the route updates. We are just saying we're adding an MD5 hash for trustworthiness. So if you're running Wireshark, you'll still be able to sniff out all the information that OSPF has to share, but you cannot inject any bad information. You cannot put a router in that network and tell everyone to start listening to what it has to say, because that MD5 authentication hash must match. So there's the commands. You can either set it globally, you can set up a message digest, and then every interface has to have it, or if you just want to set it up on one or two interfaces, just set it up on those one or two interfaces. So the commands are quite similar, but remember that once you set it up inside the routing process, you got to do it on every interface. But if you just want one or two interfaces, then you just use the interface commands. Things that will mean adjacencies will not form. The interfaces are not on the same subnet. The timers don't match. The network areas don't match. The network types don't match. Or you've just had you're missing the network statement. Or you've tried to set up MD5 and there's a typo on one of your keys. These are the first things you need to check, because unless OSPF can form a basic neighbor adjacency, it will never function. The states. So when you first fire up OSPF, it's down, it goes into initialization, and once it sees itself in other people's hellos, it goes into two-way. Then it says, right, I've got some information I need to give you. That's exchange start. Then it exchanges. Then once it's got all the databases, it goes to loading. That's crunching all the numbers, compiling the database, and then it goes to full. Like I say, in the lab environment, it'll go from two-way to full less than a second. It's very hard to see without debugs. But at a big production network, it may well be in exchange for quite a few seconds and in loading for quite a few seconds. So the exchange is swapping the databases and loading is compiling the databases. Show up your protocols, show up your OSPF neighbor, show up your OSPF interface, show IP route just the OSPF, and if you want to clear out those commands, then clear IP OSPF process. Is there neighbors? Very first question you need to ask. Show up your OSPF neighbors. Okay, you got neighbors, but you don't have the right routing information. Are you missing network statements? Does the traffic take the correct path? Once again, it could be missing network statements or routers that are down between you and them. Or passive interface. Always check for passive interface as well. Show up IPv6 protocols, show up IPv6 neighbors. clear IPv6 OSPF process, exactly the same setup for IPv4, just with your IPv6 commands. There are 5 key categories of OSPF network types: point-to-point, broadcast, multi-access, otherwise known as Ethernet, non-broadcast multi-access, otherwise known as frame relay, point-to-multipoint, and virtual links. Without the DR-BDR election process, all the routers would have to talk to each other and the flooding would be unbearable. But you got to elect that router. You got to have your election process. The router ID, the priority is the election decider, but when all the priorities are the same, it's the highest router ID. The highest router ID is either set manually, the highest loopback, or the highest active interface. Default information originate, fantastic command. Get that default route out there. Make sure you set your reference bandwidth. You don't set your reference bandwidth, your router won't be able to tell the difference between 100 meg, 1 gig, 10 gig, and 100 gig. It'll think they're all the same speed. So you've got to adjust that reference bandwidth. Timers. Timers are critical. The timers must match at each end. You can set up authentication, sort of trustworthiness of the people who are talking to you. Routers should go into full. Once they've finished their work, they should go into full. But if you've got 3 or 4 routers, the DR, the BDR, they're going to be full. But all the druthers, that's okay for them to be in two-way, because all they're doing is just listening to the DRs. That's quite acceptable. All your show commands for IPv4 and all your show commands for IPv6, exactly the same commands, just with the IP changed from IP to IPv6. And we'll see you on the next one.